Hey guys, welcome back to Explore Electronics Plus. This video is about UVM Testbench code for the verification of Synchronous FIFO. Let us get into the code and see how actually we are going to verify the Synchronous FIFO with different aspects using UVM. Here is the complete UVM code and the UVM Testbench components, and at the right you can see this is our design code for the Synchronous FIFO. Here the depth of the FIFO is 8 and I have taken the data width as 8. It means FIFO will store 8-bit values and the depth of the FIFO is 8. It will store 8 such values, right? And how actually this behavior of the FIFO and how we are going to design this, I have already explained in my previous video. You can see this video, Synchronous FIFO Design and Verification, Verilog Code and Testbench. In this video, you can see the theory aspects of FIFO, how the design will be, and which are all the signals, inputs and outputs, and the conditions for generating the empty condition and also the full condition flag in FIFO, and the design part of the code is completely explained. And also if you go further, you can see the test bench using Verilog. Now in this video, for the same design which I have taken over here, and I am going to explain how the verification through UVM code. So as we know, UVM will be having a test component. Under that we will be having environment and agent and scoreboard. Inside the agent we will be having driver, monitor and sequencer. And if we want to test this FIFO differently, we need to have different test cases which I have taken here. You can see test.sv, write read test, write then read, write read parallelly and only write. So these are the different tests I am going to perform to verify this FIFO. So starting from the test bench top, the test bench top is a module. It is not a system Verilog class or any other type. It is just a module. In the top, we are going to include all the test bench components comes under this test bench, right? We will be having a sequence item. We call it as a packet class or transaction class. And we will be having a sequencer in our UVM test bench. And we will be having different sequences to generate the data, and we have a driver to drive the transactions into DUT through interface. So we have interface.sv also, and monitor is required to get back the data from the DUT after performing its operation, and this monitor will give the data to scoreboard for checking the functionality whether it is correct or not. And there is an agent consisting of sequencer, driver and monitor classes, right? And this is the test environment. It will be having agent as well as scoreboard. So then we will be having a different test classes over here. You can see test.sv, write test.sv, write read test, write then read and write read parallel. These are the 5 test cases I am performing on this FIFO. That's why I have different test files over here. This test.sv will be having generation of the random test, and that random data will be given to the FIFO. Then we will be having a write test. We will be performing only write, and we are expecting when the FIFO is filled, we need to have a full condition high. And then write read test. This is writing the data into FIFO and reading back immediately. And the next test case is write then read, write completely and read the data completely. And here we are expecting full condition after write, and reading the complete data we will be expecting empty condition. Then we will be having another test case to test the functionality of the FIFO, whether it will able to write and read parallelly. That is the last test case. So let us get into the code now. The test bench top is a module. It will be having global signal declarations, clock and reset. And also it will be having a clock generation, starting with clock is equal to 0. And forever, for every 5 time unit, clock will be inverting. So this is the clock generation we have. Means it will be having a clock period of 10 time units. For every 10 time units, you will be having 1 clock. Then the reset is 0 first, and then after 5 time units, reset become 1. Means our DUT is response to, or it is sensitive to, active low reset. Whenever low reset is there, the system reset will happen, and we are coming out of the reset when reset is equal to 1. That's why we will be having after 5 time units, reset will be 1. From 5 time units onwards, we will be generating the different data to perform on the FIFO. Then we will be having an interface. This interface is with a name FIFO interface. it is of type interface itself. We need to instantiate this, and we'll be passing the clock and the reset what we have generated over here. So through the test bench top only, we'll be generating the clock and reset, and directly will be given that to the interface. This interface directly give these values to the DUT. You can see this is the DUT instantiation. FIFO sync is the name of the DUT, and the instance handle or the name is DUT. We will be passing this clock and reset directly to the DUT through the interface, right? And all the other signals, data in will come from the driver, write, read, and empty, full, data out are come from the driver, and through the interface we will be connecting those. This is the instance of the DUT. Then coming to the next part of the top code, that is config DB. Here this interface what we have will be consisting of all the different ports of the DUT, means the pin level information we will be having over here, and these signals we need to connect through the ports of the DUT, and this interface will be getting the things from the driver. In the driver, we need to have a facility to access this interface ports, right? That's why there is a concept of config DB over here in the UVM. So by using UVM underscore config DB, and we are passing the type of the interface we are setting, we need to use a set method over here first, and we need to set the interface handle we are having over here. Here we will be having an interface handle as in, we will be passing that, and this set method expecting 4 arguments. The first argument is a path from where we are setting, means we are setting in the test bench top, and then we will be having a star over here. It is indicating which component has to get the access of this FIFO interface. We are providing star means all the lower components to this test bench top can access. That's why it is star. And the third argument is a key we are providing. Through this key any component can access. Means whenever they are accessing this interface, they need to use a get method. In the get method they have to use this third argument as VIF itself. This is the key. And the fourth argument is the handle over here which we are using, that is in. In the driver and monitor you can see the get, and where they are getting the access of the interface. You can see in the driver directly. In the build phase we will be having a UVM config DB get method. You can see this is the get method. Here the very first thing is this, means in this component we are accessing, and this is empty. This empty, and this provides the complete path to the driver class, and then the key is VIF, the same VIF key which we have used at the time of setting the interface over here, you can see. And the last one is the handle. In the top it is in, but in the driver we are using VIF as the handle. That's why the last argument is VIF. This is how we can get the configuration interface from the config DB. Then only driver can pass the values to the interface, and interface will do the rest of the functionality to pass it to the DUT, right? So we'll be having an interface. Other than these signals, we'll be having a mod port and clocking blocks. This mod port and clocking blocks used to avoid the race conditions, and also we'll be providing the directions of the signals with respect to driver and monitor. You can see clocking block of the driver over here and clocking block of the monitor. Mod port driver, and we'll be passing the clocking block and the input signals. You can see over here with respect to driver and monitor. So in the clocking block of the driver, it is operating with the positive edge of the clock, and in the driver, data in, read, write signals are output of the driver. We will be providing the data which are all the inputs in the DUT are outputs of the driver class. Similarly, the outputs of the DUT become input in the driver, right? Driver functionality is to whatever the data generated in the sequence has to driven on the interface and to the DUT. That's why driver will be having output data in, and read and write are the outputs. And in the monitor, if you see, monitor functionality has to get the data from the DUT. All the signals will be act as inputs in the monitor. That's why we are declaring the directions over here, so that if we miss writing the assignments in the reverse direction in the driver and monitor, we will be getting an error. This will avoid that confusion, right? And in the test, the very first thing is we will be generating the random test. So here the FIFO test is a type of UVM component. So class FIFO test we are extending from the UVM test, and this is a UVM component we need to register into the UVM factory through tick UVM component utils, and we need to pass the argument as FIFO test. And under the test we will be having a environment component. So we need to instantiate the FIFO environment, and env is the handle for that. You can see the environment file name, the class name is FIFO environment, that we are instantiating over here, and handle is env. So env is equal to FIFO environment using type id create, and we'll be passing the two arguments to the create method. This create method internally call the constructor itself, constructor of the environment class. You can see the constructor of the environment class. This is also a UVM component. We registered to the factory with a tick UVM component utils, and every UVM component constructor will be having function new with two arguments expecting. One is the string name, another one is UVM component as parent. And here you can see in the test while generating that, here the name as env, and this is the parent class. This is a UVM component parent. This is how we are going to create the lower components. So coming to the environment now, this is also a UVM component which we have registered to the component utils using UVM component utils, and then agent and scoreboard are the lower components of the environment which we are creating here. And in the build phase we are creating the agent and the scoreboard in the same manner. You can see FIFO agent and FIFO scoreboard is creating, and these two are also a UVM components, and we are passing the two arguments as the name as well as this is the UVM component parent. So you can see the agent and agent constructor. After this build phase which is creating the lower components, and after the build phase there is an end of elaboration phase to print the topology. It means how the UVM test bench is created over here, and that top down hierarchy it will be printing over here in the end of elaboration. By calling print we can print that topology. Then we have a run phase. Run phase is a task. In all the components, UVM components, we will be having a run phase as a task. This run phase in the test component will be having creating the FIFO sequence first. We will be having a sequence over here. You can see this FIFO sequence is responsible for generating the data. It is a kind of generator class in a system Verilog test bench. So this FIFO sequence will be utilizing a FIFO sequence item packet. Here is the packet class. You can see this FIFO sequence item extended from UVM sequence item. This is a object type, UVM object. Even the sequence is UVM object. And this sequence item will be having all the signals of the DUT, and which are all the things we are going to randomize and going to generate the data will be represented with rand keyword. And the outputs of the DUT are just a part of the transaction class, but it is not, they are not going to participate in the randomization. That's why here full empty data out are just represented as bit with the size, and they are not belong to randomization packet, right? And which are all the things we are going to randomize will be represented with rand. So this packet of sequence item class will be utilizing in the sequence now. So this kind of sequence will be generating the data that will be started in the run phase of the test, right? You can see task run phase. Here we are creating the object of the FIFO sequence. You can see FIFO sequence is the handle over here for the sequence, FIFO sequence, and this sequence will be having generation of the data. Let us see how it is generating first. Every FIFO sequence in our test bench will be having a task body. All the sequences in the UVM will be having a task body. This body task is called whenever we are going to start that over here in the run phase. In the run phase, we will be creating this object of the sequence class, and raising the objection, we will be starting the sequence to generate the data. After the data is generated, it will go to the driver, and then it will go to the DUT. Again, it will come back to the monitor, and it will go to the scoreboard for comparison. So by raising the objection, we are starting the sequence means the run phases of all the different components are going to be started parallelly. Until that complete transaction get completed, we will be having an objection raised and no other process will disturb that. Until it completion, there is an objection, and later we will be dropping that objection and going for the next process, right? So that's why the task run phase in the test is the main thing where we are going to start our stimulus generation and transferring the data. That's why here first we need to create the sequence and raising the objection, and here you can see FIFO underscore sequence is the thing I am using here, and this we need to start on the sequencer which will be having in the agent and in the environment. We are starting this sequencer for this particular sequence, and this sequencer is available inside the agent, and agent is there inside the environment. This sequencer is not directly available inside the test component. In the test we will be having environment, and then we will be having agent, then we will be having sequencer. So we are pointing to this sequencer to start this FIFO sequence. What this FIFO sequence consisting of, we need to see now. You can see this sequence.sv, we will be having a FIFO sequence. Here we will be having a task body. This body task is defaultly called when this test is, when the sequence is started. So in the body task, we will be having the generation of the data. You can see, first we need to create the sequence item packet. FIFO sequence item is an argument here. So it is a packet class. So this packet will be having a default handle called REQ. This REQ we can create over here first. After creating, we need to wait for the grant from the driver. Driver has to give the grant so that we can generate the data and give it to the driver. Until we are receiving the grant from the driver, we are not supposed to create the data. We need to wait for that. That's why waiting for the grant. After receiving the driver request, we will be generating the data. What I am doing here in my test, I said this is a random test generator. That's why in the sequence I am just using req.randomize function. This will generate the inputs randomly, right? The random data I am giving to the FIFO and checking. And this assert is required here. Why? Because if that randomization fails, we need to abort the simulation here itself. That's why I am using assert. If the randomization fails, it will throw an error and stop the simulation. If it completes successfully randomization, then we need to send the request to the sequencer and to the driver that take this data further. And after that request completes, then we will be waiting for the item done signal from the driver again. Once the item is done, we are again move on to the next process to create the item, and again waiting for the next transaction request from the driver. So this is a way to generate the data in the sequence. This is one way. There is another way to do it. Other than writing wait for grant, send request and wait for item done, we can use start item and finish item. That we will be see in the next sequence. So first let us try to complete this part. After generating the data, after the randomization, here we have started that, it generated the sequence, and then it should go to driver now. So we need to understand the driver functionality. In the driver, you can see FIFO driver, it is extended from UVM driver. This FIFO driver will be getting the packet as FIFO sequence item, this FIFO sequence item packet. That's why we will be having an argument over here. And here in the driver, we require an interface. Driver will get the data as a packet from the sequence, and then driver will convert that into the pin level format, and it will connect to the ports of the interface, right? So to have an interface over here, we will be getting the handle from the config.db, which I have already explained in the build phase. So the build phase of the driver is to get the interface handle from the config.db, and then we need to directly go to the run phase. So in the run phase of the driver, what we need to do, whatever the data sequence has generated, that we are getting into the driver through the sequencer. If you see the sequencer code, here we will be having just a constructor inside. We have not defined any functionality of the sequencer. The UVM sequencer will take care of the internal functionality, how it should communicate between the sequence and the driver. So in the driver now we need to assume that we should get the data, means the transaction. You can see here transaction is the sequence item over here. This transaction we need to get from the port of the driver. Driver will be having a port, TLM port, that is sequence item port. This port is responsible for getting the transaction from the sequencer. So here you can see the standard function get next item. This will take the transaction from the sequencer. So sequencer should give that. So that connection we need to make first between the sequencer and driver in the agent class. In the agent we will be having driver and sequencer. So in the connect phase of the agent you can see driver sequence item port is connected to sequencer sequence item export. Sequence item export is a port of the sequencer and sequence item port is a port of the driver that we have connected. Through these ports only the transaction will flow from sequencer to driver. So sequencer port is connected to driver's port now. So from where driver has to get the data? From the sequence item port. If you see the driver run phase, from the sequence item port get the next item call and it is expecting the transaction to come. Once it comes to the driver through the port, now we need to do the driving functionality. What we are going to do here, this is a separate task which I have written here. You can write this part of code over here only. Here what I am doing, at passage of the driver's clock, we are waiting for the one clock cycle of the driver clock, and whenever the transaction comes we need to convert that into a pin level format and we need to assign that to the interface. You can see trans.wr, we need to assign that to tick driver interface WR. What this means, this macro is defined over here. Define driv underscore interface is VIF dot driver mod port through that driver clocking block. So we are pointing to the clocking block of the driver and we are assigning the write signal. We are accessing the write signal. So what is happening here means the interface write signal is assigned with transaction write data. Similarly, the transaction read will be assigned to interface read. And once the transaction write is one, we need to also provide the data into the interface. So here we are doing the assignment of transaction packet signals into the pin level format of the interface. So interface now will be getting the data from the driver here. After that, interface will take care of driving the data into the FIFO through this. You can see over here we have an interface signals and that will be assigned to DUT. This will be done by the driver. Once that is done, the monitor has to take that signals into the packet level again. It is converting that signal information into the packet level and it will give it to the scoreboard, right? This is the very first functionality which we are doing here and testing that random test by running this. Let me run this code and we are expecting the random test generation over here. And if you see in the sequence, we have a randomization over here and repeating this 15 times means we are generating a 15 data in a 15 clock cycle and we are expecting that random data to go into the DUT. And let us look at the waveform now. Initially, the reset is 0 and from here onwards reset is 1. And starting we'll be getting the randomized data as read is equal to 1. Since there is no data in, we have not write into the FIFO yet, so empty condition is 1 now. And here is the first data. You can see 22 is writing, write is equal to 1. So 22 is the first value we are writing, and in the next cycle we are making read is equal to 1. At the same time write is also happening. So the next value is generated 63. Means the first value going into the FIFO is 22, next value is 63, and from here onwards we are reading the data, and with the 1 cycle delay the FIFO will respond with 22 and 63 you can see. And after that read becomes 0 and we have, by the time we have already write the third value 9a. And when it is reading again means here it is reading, right? That's why the third data is coming out here as 9a. The first data is 22, second data is 63, third data is 9a. 22, 63, 9a has come out. when it is reading. And by the time already the fourth data is written into the FIFO as 4C, and the fifth data is written that is 45, and the next data is 5A. To see that, we need to continue our simulation further, and we need to see whether the data 4C, 5, 45 and 5A are coming out. But we are doing only 15 repeat transactions over here. Means this will allow us to have a 15 clock cycles over here, so that it will show only the read generation up to 3 values. Here 2, 2, 6, 3 as well as 9A we are comfortably getting out. Since it is a random data generator, we are expecting this much only. That's why we need to have a complete write and read transactions, or write read back to back, to have a complete functional verification of this FIFO. So to have that, we can directly comment this, and we can check only the write functionality. This test case, FIFO write test, will be for writing the data into FIFO. So you can see over here we will be having the write test. This write test, if you see, is again a component, and we are declaring it to the UVM component utils. And this FIFO write test I have extended from FIFO test itself, right? This FIFO test is my parent component now, and that we are expecting a child class as FIFO write test. That's why there is no build phase here separately. Directly I will be having a run phase, and there is a constructor here. Inside the constructor I will be creating my sequence component. This write sequence is the separate sequence which I have written for this test. You can see the sequence. Here we'll be having a second class, that is FIFO write sequence, extended from UVM sequence. Here I am generating the random data again, but I am having a constraint, inline constraint over here, that write is equal to 1 and read is equal to 0. It means our idea of this particular test is to only write the data into FIFO. To have that, I will be having a sequence called FIFO write sequence. That sequence I have written over here, and this will be having a FIFO sequence item as item, and in the task body again I will be generating the data. First what I need to do, I need to create that item. You can see there is another method of generating the data and communicating to sequencer and driver, is start item and finish item. In between we will be generating the data. In the previous case we have used wait for grant, send request and wait for item done. In this case I am using the another method called start item and finish item. Here is the create method to create the item first, this item, and then we are starting the item with passing this item, and this will do a function call internally for wait for grant, and it will wait for grant, it will get a grant and allow us to randomize, right? You can see over here after the start item we are randomizing it. And since the sequence generation is only for the write thing, when writing the data, here item.write is equal to 1 and item.read is equal to 0. This is the constraint I will be having over here, and I am randomizing other things. After this there will be a finish item. This finish item internally call this send request and wait for item done, right? So this part of the code which we have done in a start item, randomize and finish item. So if we run this particular test, you can see the write test. After this we will be having a run phase where we are starting that particular sequence, right? It will start this write test sequence. So now I am running this test. If you run this test, we will be expecting only the write data to be generated and read signal will be 0, and it will generate the 8 values. You can see the sequence again. We will be having repeat 8 transactions over here. So we will be generating the 8 values and we will be expecting the full condition after it reaches the depth of the FIFO. You can see initially the FIFO is empty and reset is 1 over here, and write is equal to 1. As soon as write is equal to 1, we started giving the data. Data in is 4D, the second data is BA, then 94, and once the first data is written, empty condition is going low, and we will be having 94, DB, 8F, B0, 3E and 39 are 8 datas. 1, 2, 3, 4, 5, 6, 7, 8. Now it reaches the depth of the FIFO. No further data we can write. That's why full condition is 1. This is our second test case. We are verifying the FIFO full is 1 after writing the 8 values, right? This is also coming correctly. This is working for writing the data completely into FIFO. Now the other tests are write read back to back, write complete then read, and also write read parallel. This we will see in the next video, and we'll check all the other functionality of the FIFO through these 3 test cases. Thank you.